So right here I've got an interesting piece of kit called a theremin, which is actually a musical instrument, a synthesizer to be a little bit more specific. And the cool thing about this instrument is that you can play it without physically touching it. So the way that you do this is, you can see we've got these two antennas sticking out of the device, and those are actually proximity sensors, and they can sense how far away you are from them. And so by changing the distance between usually your hands or fingers and those antennas, you can change the sound that it makes. So this antenna, for example, controls the pitch, and by getting closer to it, you make the pitch higher. And this antenna controls the volume, and by getting closer to that one, you make the volume lower. And so by moving your hands relative to those two antennas, you can make music. That is, if you're actually good at playing this, which I'm not, because I made this thing like a week ago and haven't practiced much. Also, I'm just generally bad at making music. But I've wanted to make a video about these for a while now, because the electronics inside them are actually rather interesting. So that is why I've built this prototype, so we can take a look at how exactly this works. We can see all the components. We have the schematic. So let's just get straight into it. The theremin was invented well over 100 years ago by a Russian inventor named Leon Theremin, although that is apparently his Western name. It's something different in Russian. I don't know exactly how that works. If you know, please explain in the comments. But what I think is cool about this invention is how, even by today's standards, well over 100 years later, it's still a very unique and fascinating instrument. So now the question is, how does it actually work? Well, first of all, you should know that naming these things antennas is kind of confusing, because they're not actually radio antennas that are transmitting or receiving radio signals. They're actually just sense wires, and more specifically, they're just one side of a capacitor. So if you have a capacitor, right, a normal capacitor is two plates, two conductive surfaces with an insulating material in between them, which is referred to as the dielectric. And then you can charge this capacitor, you can build up charge on those plates, you get an electric field through that dielectric, and that way you can store charge in that device. Now with a capacitor, the closer you put those plates together, the less distance there is between them, or the thinner you make the dielectric, the greater the capacitance becomes, so the more charge you can put into it. So in this case, essentially the antenna is one side of the capacitor, one of the plates, and you, or your fingers, are the other side, or the other plate of the capacitor, and so the air in between is essentially the dielectric. And so what happens is, when you get closer to one of those antennas, you make the dielectric thinner, and so you increase the capacitance, and it is that increase in capacitance that is sensed by the electronics, and that ultimately results in the sound of the instrument changing. So you could say that when you're playing the theremin, you're actually playing music by manipulating the electric field, which is pretty sick. So before we continue and dive into the electronics of this device, I know a lot of you like to see things being demonstrated. So here is some footage of me attempting to play something on the theremin. So, I think we can all agree that I need a little bit more practice on this. So let's just move on to the electronics, because I'm actually slightly less bad at making electronics than I am at making music. So the first thing we need to make a theremin is essentially a tone generator, right? Something that generates an audio signal in the first place that can then be manipulated using those two antennas. So how can you generate an audio signal? Well, generally you can use something called an oscillator. So an oscillator is a circuit that just produces an AC waveform at its output. And a very simple oscillator circuit might look like this. So you just take an operational amplifier, you add a few passive components, and it just produces a square wave output signal. Now, the output frequency of this oscillator depends on the values of those resistors and capacitors that you use. So let's say that we take that capacitor and remove it from the circuit, and instead replace that with a sensing antenna. So now essentially you've got a variable capacitor whose capacitance changes based on how far away your fingers are. That means you now have created a super basic, crude theremin, because depending on the distance you have from that antenna, the capacitance will change, and so the frequency of that oscillator will change. So, yeah, you're getting somewhere with that. But unfortunately, this circuit has a lot of problems, and one of the major problems, actually, with this thing is that it's the opposite way round from how an actual theremin works, because remember, on this theremin, the closer you get to the antenna, the higher the pitch becomes. Whereas with this circuit, the closer you get more capacitance, and that will actually lower the frequency of the oscillator, so your pitch is going to go down. So this is a sort of an inverted theremin, I guess. Not really what you want. So instead, what you actually do is you take two of these oscillators, like this, and you connect the outputs of those together using a couple of high-value resistors. I'll explain why that is in just a moment. So right now at the top we've got the variable oscillator, which has the antenna wired up to it, and at the bottom we've got the reference oscillator, which is just operating at a fixed frequency which never changes. There is also a couple of potentiometers in them so that you can fine-tune the frequency of both oscillators, because you can't rely on fixed resistors for something like this, because there might be slight differences in them and then you'll never get it right. So you have to have some way of tuning the circuit properly. The key to how this works is that these oscillators are going to oscillate at slightly different frequencies, because the one at the top, the variable oscillator, has a different capacitance because it has that antenna connected to it. So let me use a simple example to illustrate what's going to happen here. Let me play for you a 1000 Hz tone. Okay, not too spectacular, right? Now let me play for you a 1001 Hz tone. Still not very interesting. It sounds pretty much exactly the same because it's such a small difference. But watch what happens, or I guess listen what happens, if I play those tones at the same time. They start interfering with each other, and so you get this sort of varying amplitude thing. And the interesting thing is that the amplitude varies once per second, or 1 Hz is the frequency at which this variation happens, which happens to be exactly the difference in frequency between those two tones, 1 Hz. So the same thing is going to happen in our theremin. So in this case, both of these oscillators are designed to oscillate at a relatively high frequency. So I think this one sits somewhere between 150 to 200 kilohertz, depending on how you set those potentiometers. So let's say the reference oscillator is oscillating at 200 kilohertz, and the variable oscillator is oscillating at 199.5 kilohertz. Well, that means the output signal is going to vary in amplitude at 0.5 kilohertz or 500 hertz, and that's the tone that you're going to hear in the output. And so now, the closer you get to that sensing antenna, the lower the frequency of the variable oscillator will be. Therefore, the larger the difference between them is going to be, and the higher the frequency of the output signal is going to be. So that is how it works. So then what about those 100k resistors that are used to connect the outputs of both oscillators to each other? Well, the reason we need such high-valued resistors here is because otherwise the oscillators will actually start to synchronize to each other. I had this happen when I used much lower resistors. I think I used like 22k or something. what actually happens is the oscillators start to synchronize, which of course is something you want to avoid because the whole point of this circuit is that they oscillate at different frequencies. So that is why you need those sufficiently high output resistors. Now this does present a new problem though for the next part of the circuit, because the thing is the signal that comes out of this is not ready yet to use as an audio signal, because yes, it has this varying amplitude that we just discussed, but ultimately it is still a high frequency square wave, and we need to get rid of that high frequency carrier before we feed it into any audio equipment. So we need to clean the signal up a bit. And you can do that with like filtering components and stuff. But the problem is if we're going to hook up components to this output signal and start loading this output signal, well, that's going to affect the signal a huge amount. It's going to attenuate it by a huge amount because that signal comes through these massive 100k resistors, which is a very high impedance. So introducing just a little filter or something like that on this signal is going to completely ruin things. So what I need to do first is you need to put a buffer amplifier on this, which is just an amplifier with a gain of 1, and all that does is just copies the signal as it is straight onto its output. But then the output impedance of this amplifier is much lower than 100k, and so from this amplifier we can safely start loading the signal, drawing current with a bunch of components without affecting the original signal that comes into the amplifier. So what we need to do first is we need to remove that high frequency square wave carrier, because we don't need that for an audio signal. Actually, we don't want that because it's just going to create noise. So what we do is we use an AM detector, which is just a diode and a capacitor, to essentially rectify it into a varying DC. So that strips off the high frequency square wave carrier and just leaves us with a nice varying amplitude, or a nice varying voltage, which is ultimately going to be our audio signal. Then we also use a series capacitor to strip off the DC component and essentially shift that waveform to make it AC instead of AC on top of some DC component, which again, you don't want to feed a DC component into an audio system. And then finally, we also use a low-pass filter to filter out some of the high-frequency noise a bit more, to get a bit of a smoother output. Now actually what is important to realize about this filter and other filter stages in the circuit is that you can use more or less filtering depending on your personal taste. So you might have noticed that my theremin has this sort of harsh electronic sound to it because I don't use all that much filtering. If you used more aggressive filtering, maybe some more stages of filtering, you could create a smoother output waveform that sounds more like the sort of original theremin. But I liked it this way, so I made it this way. You can do that differently if you decide to build your own. And that basically gives us our audio signal with variable pitch according to how far away you are from the antenna. So now what about volume control? So the volume control circuit that I came up with is kind of a complicated and confusing mess, so I apologize for that in advance. I'm going to try to explain it anyway. There's probably easier, more elegant, better ways of doing it, but here's what I came up with. So first of all, we're going to repurpose the output signal of one of our oscillators that we saw earlier on. So if you look at that schematic, you can see there's a little wire coming off the bottom called reference, what is it called? Reference carrier. That's just a little tap off from our reference oscillator that we're going to reuse for the volume control. So what happens is, first of all, we send that through a 470k, so again relatively high resistance, and then connect that to our sensing antenna. And again, our antenna is just a variable capacitance. So that means the voltage in this point, so where the antenna connects to the 470k resistance, is going to change depending on how large that capacitance is. So if you get closer to the antenna, you're increasing the capacitance, which means the impedance of that capacitance for the high frequency AC signal will get lower, which means the voltage in that point will also get lower, or the amplitude of the voltage in that point will get smaller. Now then that signal once again goes into a buffer amplifier to prevent the rest of the circuit from loading it, so again just an amplifier with a gain of 1, and then it gets rectified by once again an AM detector circuit, just a diode. Except this time the diode, as you can see, is put in reverse, so it's pointing the other way. So we're not rectifying it into a positive DC voltage, we're rectifying it into a negative voltage. And so, and I have to say this right because this circuit flips things around a bunch of times and that makes it confusing, when you get closer to the antenna, the AC amplitude gets smaller, and so the DC output from this circuit gets less negative, or closer to 0. Now, this negative voltage then goes into a so-called summing amplifier circuit, along with a positive DC voltage that you can set using a potentiometer. And as the name of the circuit implies, the summing amplifier takes those two voltages and adds them together. But to make matters more confusing, it also inverts it, so it also multiplies it by -1. So here's a little example. Let's say the negative voltage that comes out of our circuit is -2, and we've set our potentiometer to +3 volts. So we're going to add them up. We get 3 plus -2, or 3 minus 2 is 1, so the output of the circuit would be -1. Now let's say you moved your hand away from the antenna, so the negative voltage would become more negative. What would happen now is, let's say it's gone down to -3, so you add them up again. The potentiometer voltage is still going to be 3 unless you've changed it, but let's say you didn't. It's going to be 3 plus -3 will be 0, and so now the output will be 0. Now, to make matters a little bit more confusing, this summing amplifier doesn't have the same resistance in its feedback loop as in the on the input side, so it also multiplies by a large factor, right? It also has gain to it, so it has a gain and an offset, which you can set using that potentiometer. Ultimately, what it all means is that the further away you move your hand from the antenna, the closer to 0 the output of this summing amplifier gets. So the output of the summing amplifier is usually somewhere around -4 volts, and the further away you pull your hand from the antenna, the closer it gets to 0 volts. So the summing amplifier kind of flips things around again, if that makes sense. Now the output from that summing amplifier then goes to the next part of a circuit, which is actually a regular amplifier again. So you can see we've got an operational amplifier, and into that goes the audio signal that we just created using our oscillators. Now the gain of such an amplifier is normally set by using two resistors, so the values of those resistors determine how much amplification there is. In this case, one of those resistors is replaced by an N-channel JFET, which is kind of like a variable resistor in this application. And the way this JFET works is when you apply a negative voltage to its gate, its resistance goes up. And so in that case, or in this particular circuit, if we apply a negative voltage to the JFET's gate, that would increase its resistance and that would lower the gain of this amplifier. And now that gate, you might have guessed it or just seen it from the label in the schematic, is connected to the output of our volume circuit, so that if you move your hand away from the antenna, your output voltage on the summing amp gets closer to 0, which means the gate voltage on the JFET gets closer to 0, which means the gain of the amplifier gets larger, which means the volume of your output signal goes up. So that means moving away from the volume antenna gets you higher voltage, also higher voltage, I guess, higher volume on the output. But that is the volume control circuit. It was kind of a pain to design. It's a complicated mess, but I guess it works, so that is nice. Now, the physical design of this theremin is of course rather straightforward. I just soldered all the components onto a prototype board. I put a piece of plexiglass over the top of it to sort of protect it a little bit and of course make it look very fancy, and the antennas are just regular pieces of copper wire. Now on real life theremin's, they tend to be a bit bigger and they use bigger copper tubes as the antennas instead of just thin wires, which actually would help in giving it more range, so you can be further away from the antennas. But I wanted to make sort of a small scale version because I don't have a lot of space to put a full size theremin, so that's the reasoning for that. I think one thing that could be better about this thing is I think one mistake that I've made is I've placed the volume and the pitch antennas quite close together, so you can actually hear when you approach the volume antenna that not only does it change the volume, it also changes the pitch a little bit, which I think is because it also slightly changes the capacitance of the pitch antenna because it's too close to each other. So if I were to do this again, I'd probably have it like this and just put the volume control antenna all the way on the other side to avoid that problem. Something else that you could change about this is of course the filtering. You could apply more aggressive or more stages of filtering to create a different kind of sound from this thing, because right now it sounds like a pretty harsh electronic theremin, whereas you might want the more classic sound that you might be used to, at least that is if you knew what a theremin was in the first place. So anyway, there it is, the DIY theremin and all about how it works. If you want to build it, you can, because I'll put all the schematics online. There will be a link in the video description. I hope you've enjoyed this video. If you did, then maybe consider subscribing to this channel. And of course, thank you very much for watching.